Hey, well, for those of you who don't know me, I'm Ken Kurtz, faculty in psychology and part of the COCO program. And I have the honor today, as a psychologist, of introducing a professor of psychology, Jay Dixon, who now spends lots of his time talking to physicists and chemists and other interesting folks. So Jay actually started out in the SUNY system as an undergrad, so that's always fun at Albany. And then he went to Madison for his PhD in psychology. And now he's directing a center for the study of perception and action at University of Connecticut. And he's going to talk to us today, let's see if I can say all his words, about rudimentary perception action in dissipative.
Very good. Well done. Thank you very much, Dan. And thank you for the very kind invitation. I've had a wonderful time here so far. I look forward to getting to know some more of you as the day progresses. I'd like to tell you today about some work that we've been doing on systems that are not alive, and yet which we think might have something to say about living systems. So we are, in a sense, trying to sneak up on biology without making contact, quite yet at least, with systems that have been evolving for 4 billion years or so. So the general strategy of what you're going to see today is to try to find systems that are in the same physical class as biological systems, but are not alive, and to show that those systems are end-directed in a particular way, and that with some slight changing of the boundary conditions, we can actually make them do things that we would normally think about as being hallmarks of living systems. Before I start, let me acknowledge my collaborators, Bruce Kay, who is a senior scientist in our center, and Dilip Kandapudi, who's actually in a chemistry department, but is a physicist trained with Ilya Prigogine in the sort of heady years just after he won the Nobel Prize. So organisms are a particular type of physical system called a dissipative structure. Dissipative structures kind of famously, at least in my world, maybe not in everybody's, but famously form in response to gradients. When a gradient is applied to matter in some configurations, you'll get the sudden spontaneous emergence of a physical form. So we think organisms are one type of dissipative structure. So we might have the larger set of dissipative structures, which we'll represent here with this blue little Venn diagram. So things like tornadoes, for example, are dissipative structures. A particular set of conditions hold in weather, a very strong gradient, and the tornado itself pops into existence in order to help dissipate that potential energy. Hurricanes, also in the weather domain, are also recognized as dissipative structures. And they too simply come into existence, run their course, and are short-lived. The Belousov-Zhabotinsky reaction in chemistry, here shown in sort of an open configuration where we get all sorts of beautiful patterning in waves, is also a classic dissipative structure, as is Rayleigh-Baynard convection. So these are Rayleigh-Baynard convection cells. Inside of this set is the set of organisms. So organisms are part of this larger set. What we're trying to do is get closer and closer to the boundary of this set, right, by showing that dissipative structures can do things which are very much like what living systems can do. So one thing I'm going to try to convince you of today is that at least some subset of dissipative structures, maybe not all of them, but at least some subset, are end-directed. And by this, I mean something very particular. That is, at least from a physical perspective, what they seem to be doing is to function in a way that either maintains or increases the rate at which they consume energy, which we're going to index through the rate of entropy production. Sometimes I'll call it REP, sometimes we'll refer to it as sigma throughout the talk. I'll hopefully delineate those for you. In doing so, it will undergo changes in structure and sometimes behavior in order to maximize the rate at which entropy is produced. And I'll show you examples of both of those. A key element of this argument with regards to biology is that by increasing the rate of entropy production, the system actually increases its own stability. Right? So the more energy that's going through the system, loosely put, the more stable the system is. So the system starts to generate its own persistence by maximizing the rate at which it's consuming power, essentially. So we end up with a physical principle that gives us this overarching behavior that we see in biology, in which systems seem to behave so as to maintain their own existence. Right? Behave so as to persist. A famous line from the autopoiesis people, but without the physical underpinning, right? We say there's actually this physical underpinning. What's happening is the stability is being driven by, is a product of obeying this one physical principle, increasing the rate of entropy production. Right? So this, for us, is going to be a crucial tie-in to try to explain where the sort of the driving force for biology comes from. The other thing I'm going to try to convince you of today is that we can actually have phenomena that look a lot like sensation/perception, that is, information about the environment, can be made manifest on the dissipative structure, can actually impact the dissipative structure through the use of very, very simple sensors. In fact, sensors sort of fall out of the system naturally. So sensors, in the story I'm going to try to convince you of, simply fall out of heterogeneity in the materials that make up the dissipative structure. And so that'll be sort of the second part of the story. So first, let me introduce you to a dissipative structure. Maybe some of you have never even heard this term before, and this is a pretty standard example of a dissipative structure. It'll give you a sense of what this sort of phenomenon feels like. So we have a source electrode in red here that's spraying about 20,000 volts of electricity down onto an oil surface. Right? There's actually oil in this little dish. You can see here the actual thing happening. All right? The beads here, right, which are formed into a tree structure there, and we'll be here in a minute, are just ball bearings. They're sitting in this bath of canola oil, and the ring is simply a grounding electrode. And what happens is we go from the beads just sitting in the dish, right, we apply this very strong flow to it, right, and we get this sudden emergence of a new structure. Right, so these tree structures just pop into existence like this. Right, and you can see they move around, they're quite dynamic, and they look, at least on the surface, kind of like things which are alive.
So there's actually current flow through this?
Right, yes.
So you're doing this in a vacuum?
No.
Then how are the electrons propagating through air?
They're not. They actually are. It's ionization. They're actually stripping off the ions out of the air molecules. Yes. Yeah. There's a huge resistance there. Right, so here we are in our initial condition. All right, 12 seconds in, 40 seconds in, 44 seconds in, and the reason I do 40 and 44 is that this is the threshold where we now have the structure formation. Right? If we were to compute, and we do, the rate of entropy production, it's simply the voltage, V, times the current I, divided by the temperature in degrees Kelvin. Okay, so when we're talking about the rate of entropy production, we're talking about phenomenological entropy, not a statistical entropy. Okay, so this doesn't have to do with disorder. It's literally the waste energy coming out of the system, if you will.
So the oil is not conductive, right?
The oil is not conductive. The oil is an insulator, and if it weren't, this wouldn't work. So both the viscosity and the fact that it's insulating is important.
Okay, so basically, this is optimizing to maximize the current through the system.
Exactly. Right. And in fact, we could neglect these other terms because there's literally and disappointingly no temperature change in the system that you can measure with even a $20,000 camera, should you go and foolishly buy one, thinking that there would be such a temperature change. So there is no temperature change, which I guess is good because it simplifies things, and we're holding voltage constant. All right, so really we can talk about current and the rate of entry production simultaneously. Okay, so here is what the rate of entry production looks like. So this is how we started, right? This is the onset of that dissipative structure. And this is a classic phenomenon in dissipative structures where you have a sudden jump in the rate of entry production when the structure has its onset. Okay. So now we have much better flow through the system. There's much better current going through. Okay. All right, so this is the basic phenomenon, the basic setup. And this is one of the major systems that we're studying. We also have a chemical system that I'll introduce in a few minutes.
What is the y-axis?
So this is sigma, which we're just using to stand in for the rate of entropy production, which is, again, the voltage times the current divided by temperature.
So are these configurations truly optimal in the sense that if you manually tried to optimize the rate of current flow, you couldn't do anything significantly better than this?
That's a good question. So let me defer that question just for one more slide, and I think we know part of that answer, maybe not all. So we were interested in whether that question, right? Why does this system take this tree form? Right? Why is this the optimal configuration? Are there other configurations that would be better? Or is this kind of the best that the system can do, given at least its initial conditions? Right, so one thing that we always see is trees that are reasonably long, right, quite long. Right? We never see trees that are a multiplicity of trees, but all short, for example. Right? And so we were wondering, is that just a function of the initial conditions, or is that like a property of the system? Like it's really, the system is doing some sort of optimization. And so we had the intuition that this really is an optimization of flow through the system. But you know, how many initial conditions are there here? Right? Well, there are all these beads. They could be anywhere. Right? So that's a bit of a problem. And it's very difficult to control their exact placement. So one thing we can do is we can look at least at tree lengths that we set up. Right? Now we don't have to let it spontaneously form. We can actually put it under our control and form it ourselves. So what we did is we fixed the voltage at 22 kilovolts just to pick up bigger voltage. And then we took 20 beads and we essentially built trees ourselves. And what we're measuring here, again, is simply the rate of entropy production at different tree lengths. So 20 beads, so the same amount of metal in addition for all these different runs, but arranged into trees of different lengths. So when we have a length 20, well, all the beads are in this one tree. Right? When 10, we have two trees that are each 10, and so on and so forth. Right? So here, for example, we have 4 trees of 5. See what I mean? All right. All the way down to where we have singletons. Right? They're all single beads just lining the dish, all 20 of them. Very, very hard to rift, as it turns out. But we did it. Right? So what happens when you actually just run this and take measurements of the current is indeed the longer trees tend to have higher current. Kind of circumstantial evidence that this is like an optimization. Right? It's moving towards an optimization by going towards longer tree lengths.
How high is the the ring relative to the bead height?
It's quite high. It's probably half. It's probably a centimeter.
So most of your current is occurring through the ions,
Oh,
correct?
yes, and quite a bit of it is going directly to the ring.
So you're skipping, passing over the beads.
Yes. Yeah.
Did you try measuring like the voltage difference between the two electrodes? I mean, intuitively, this would you would be minimizing potential energy. I mean, the system would try to find the lowest energy state.
Yes. Right.
And this actually kind of intuitively it kind of makes sense if you think about ions flowing because, you know, obviously like if you had a ring, that would be bad because you would build up ions trying to flow across the beads. So once you've got some blockage, you might as well just extend that all the way out. So there's something I think somewhat intuitive that you do something.
That it would do something like this.
Yeah.
Good, because there are other configurations that don't work quite as well as this, and so I might be interested to find out what I'm not sure I'm following you exactly, but let me try to get to your intuitions later because so for example, you can have just a linear ground electrode. It kind of works, but it isn't so great. So maybe what you're suggesting is a reason why that happens. So this is a setup in which, this is the most extreme setup in which we have tree length 1. So we have 20 beads along the surface, right? So we've now set the initial condition to something we don't ever see, wondering whether that will if we deliver a perturbation, will we see that again, essentially? Will it just relax to that state? Or will it relax to a state which is a higher current state, a higher rate of entropy reduction? So what we're going to do is we're just going to tilt this dish. Pay no attention for the moment to this hole in the tray. That's actually there to put a magnet in, that's for later. Actually, it's beneath the surface of the petri dish here. All right, and you can see what happens is that they don't relax the singletons. They actually form longer trees, and if we do this repeatedly, we get increasingly long trees. Okay? It doesn't go all the way to 20. There seems to be some other constraints involved, but it will always go to longer trees, and it doesn't go the other way. So when we look at that data-wise, so here is how we had started them out, 1, 2, 5, 10, and 20. Right? This is sort of pre-perturbation, this is post-perturbation. You can see that at least for 10 and lower, they always end up after perturbation with longer tree lengths than they started with. Something funny is happening here, at least from our perspective, because this is against how we think things should be operating. At 20, we seem not to be able to get good stability at 20, and we lose a couple of beads. And we're not really sure why that is. Right? It could be that there just isn't enough flow through the system to maintain a 20 bead tree in a stable configuration. Right, so we seem to be seeing structure formation that tends to go to configurations, right, morphology that changes so that it's increasing the flow through the system. So that is again to this end-directed idea that the system is trying to maximize a particular physical property. Now we've kind of gone with the rate of entropy production that has a bit of a history in dissipative structures. It may not be the right quantity, and we're certainly open to the fact that there's been a long debate about maximizing the rate of entropy production in the physics literature. But for now, that's sort of the best variable we have to measure. Let me tell you about end-directed behavior. Not only do we get these morphological changes, but the system actually behaves as well. Right? So it has a lot of dynamics to it. I'll show you this very, very simple setup, sort of our first attempt to try to get at whether the behavior of the system is end-directed. Here we have a tree. This is just a static image at the moment. Right? So we have this tree that is formed. It's going to settle in to a particular region. Okay? So whatever it wants, right? And that, in this case, is mostly under having much of its branching structure right underneath the electrode. Right, now this has started, so we're going to tilt the dish by 5 degrees for a set amount of time. What you're going to see is that the tree structure is going to maintain itself. but given the tilt, it's now going to slide down a little bit. There's the hand of God. Right, we get our tilt. We go back. Right, and now, over the course of the next few seconds, it restores itself to its previous position. All right, now if we look at the rate of entropy production, right, here's pre-perturbation, here's the perturbation event, which kind of goes crazy because we've actually moved the ring closer to the source. So this data is kind of not worth talking about, right? But here's post-perturbation, and you see what happens is that we have a slow relaxation back up to the previous level as the system moves back to its preferred region. So again, the behavior of the thing seems to be end-directed in the same way that it is morphologically. That is, it's trying to maximize the current going through it, or the rate of entropy production. Right, so by moving back to the preferred region, it restores its previous level of entropy production.
What's the rate of entropy production when you remove all the beads?
It's lower, you know, and it's relatively constant. The system can be a little bit noisy, but yeah,
not like orders of magnitude.
No. It's not a huge, you know, relative to that massive ring with its very sharp edge, right? Which, you know, the ions like a lot. It's not a huge gain. I mean, it's quite measurable.
Oil is actually helping there. If you remove,
oh, you mean even without the oil?
Yeah, if you take all the oil out.
Well, I mean, so the oil is actually covering part of the ring. So if you took the oil out as well, yeah, I mean, it's still not order of magnitude higher. I mean, but the oil actually, as it blocks some of the ring, brings it down a little bit. Okay, that makes sense. Okay, so if we can sort of up the ante on that experiment and create a situation where we have an asymmetrical location for the source. We've now moved it off center, which means that near that source, we'll get higher rates of entropy production than farther away from the source. Right. So we, at this point, are going to gate the tree, literally block it so that it can't go kind of ambulate around the ring. Right. So it can't move around the ring with two high-tech soda straws. Okay. So they're actually little slits in them. We slide the straws over, and we literally are locking down the system in its configuration. Okay. After a few minutes, we're going to remove that constraint, and should the system, whatever you want to talk about, choose to, decide to, it can move out if it so wishes. Right. We then replace the gate and see what the tree then does. All right. So here that is. So first, we're going to have the tree constrained, lock down the straw. Notice that the source electrode is off-center. Right, so this is a richer energy region than where it currently is.
Is this chaotic? Swinging back and forth?
I can tell you that it is oscillatory, but not beautifully so. So whether it's a chaotic oscillator, I don't know. We probably have the data for that. Right, so what you can see is when we release the tree, right, it moves over and eventually makes its way underneath the source electrode. Right, so in a way, the same point made a little bit more dramatically here. The system moves to regions that give it higher rates of entropy production when it is allowed to. Right, so you can see here's the rate of entropy production when it's constrained. Here's the movements of the gate. Right, so this is put my hand in there, rate of entropy reduction goes bad, but then once we have the straw back on, you can see it's very nicely, as it's moving underneath, right, we get a very nice increase in the rate of entry.
Question?
Yep.
If you move the straw that's further away from the beads, does it go towards the open gate?
So if we were to go, we were to remove this straw?
Right.
Yes, it would do that too. Yeah.
If it was on the right side and you removed the left straw, would it go back to the left side and go find?
So if it was, you want me to start here or here?
Well,
The
okay,
beads
so
are
if
here?
It was lower.
If-
If it was on the lower side of the gate, right?
Yeah, on this side,
Yeah.
like where I'm pointing now. Yep.
Right. And then you remove the opposite straw.
This
the higher
one.
The higher one. Yep. On your picture.
Okay, this one.
Yeah, that one.
Yeah.
Would it go that way?
So if it were down here, I'm not sure I understand.
So
I'm sorry.
you have your gate like this, right?
Yeah.
If the beads are down here and you remove this straw, does it go up that way?
So if I remove either of these gates and the beads are inside, it will escape that way.
It will find it and go.
Yes, it will. Yeah. Yeah.
But once it's gone, the gates still have an effect.
No. No, I mean, so the story is slightly more complicated than as I'm portraying it here, because actually what there is there's charge buildup on the surface of the oil, so it won't stay forever underneath here. Right? It actually will move around to collect more charge on the surface of the oil, which really surprised us at first, but turns out to be how this system works. We thought that it would always simply go here, stay here, maximize, be done. But that turns out not to be the case. You get buildup here that is where you now have literally attractive forces which are pulling the system back around.
So that's oil on water or oil on glass? Or
It's oil, and this is plastic surface, and it's just canola oil that you buy at the supermarket.
Yeah, is that what was going on there when it was kind of oscillating on its way to the voltage source?
Yeah, we think so. Yeah, I mean, so the oscillatory behavior seems to be all about picking up charges that are. It seems to be about the charge distribution on the surface of the oil. That's our best guess at the moment. We thought for a while that it was something about the oil flow, because there is oil movement, but that does not seem to be the case.
So you need to find an oleophobic conductive surface and see if that changes.
Yes, right. So this is a great idea. I mean, that's why we have chemists. So yeah, that's a great idea. Yes, you should see the looks on their faces when we ask for these things. Okay, so that is a case in which we have the structure moving itself into regions that give it higher rates of entropy production. Right, so that's the end-directed part of this the story. Okay, so the system seems to be driven to finding regions, finding conditions, finding configurations that maximize the rate of entropy production, and that's all good. But in biological systems, we know that there are these secondary gradients that are, for want of a better term, providing information about the environment for the system. Right? So in biological systems, right, you're not literally physically attracted to your food. Right? That would be really unusual. Right? They feel that way sometimes, right? Like the chubby hubby ice cream is calling you, but it's really not. Right? There's something else going on. There are these secondary gradients that you're using as information about environmental structure, about, in a very low-level sense, about where the energy sources are. Right, so we want somehow to have our system be sensitive to gradients other than the primary gradient that is maintaining it, that has allowed it to form. Right? We've already shown that it's sensitive to that gradient, but now we want other gradients in there too. So we had no idea how to do this at first. And we took just kind of a flyer thing. Well, maybe if we just put some heterogeneity in the story, that will be enough to get something that functions like a sensor. So what if we were to take another type of bead, right, that is sensitive to a different gradient, put it in there, they all form as a dissipative structure, we see what happens. Okay, so the story is going to go like this. We're going to make dissipative structures, right, that are sensitive to gradients, that have an element that is sensitive to a gradient other than the primary gradient, or I should say in addition to the primary gradient. It's a very abstract way to say it, but essentially we're going to try to engage that one element by a secondary gradient in a way that affects the flow through the whole system. Okay, so again, we'll make it too abstract, let's be concrete. So we are going to have, in this first set of examples, a set of beads that are aluminum, non-ferrous material, right? So not sensitive to magnetic field, which is where we're going in a second, and one ferrous element in the system. So obviously only that ferrous bead with ferrous material in it is going to be sensitive to magnetic field, but all the beads are of course sensitive to the electric field that forms the tree. So here is this situation, the bead at the tip, and we've put it at the tip purposefully, is ferrous. All the other beads are aluminum. This is a DC magnet with a great big steel washer to help spread the field out, so it's not quite so awful. Magnetic fields are kind of a pain to work with. Right, so here, the system, the magnet is off, tree is formed, it's moving around, and we're going to turn it on, and it's subtle. But there are two important points. One is there are at least a set of parameter settings we can have where the element doesn't just get ripped out, and it actually is controlling the whole system's behavior. So one element is sufficient to control the whole system's behavior, even though the other guys could care less about there being a magnetic field. Right? It's kind of a small step. And we were both excited and a little bit underwhelmed by this. Because so you have something, it's got a magnet, you have forces that are holding things together, and you pull it over there. That didn't seem like quite enough, but maybe a step in the right direction. So our next step was to, again, kind of go back to biology as a touchstone and say, well, what we really want is, in addition to just having an effect, right? So this is kind of where we are now. We've got this ferrous bead, we've got a magnet, and indeed it is affecting the entire system in ways that we can measure and quantify. We want the system to be in kind of a state of poise. Right? We don't just want the system to be pulled around by these gradients. We want it actually to be necessary that the system is somehow using some of the other energy around to get this done, right? To do whatever behavior is being suggested, is being defined by this other gradient. Right? So we want the sensor to somehow direct behavior, not just pull the structure around. This seemed like an additional difficult step that was going to be very hard to do. But we took a little bit of a flyer and decided we would try to do this. So the way we made this work experimentally is we simply took our single ferrous bead, we put it in our oil bath, and then we adjusted a magnet, right, to the smallest distance at which it no longer affected the ferrous bead. All right, so picture that we are adjusting this thing, sweeping it around, right? And if the one bead sitting in the oil, right, no power or anything, moves at all, we bring it down a little bit more. Right? So we're finding this threshold where we don't get any effect on the bead. Right? So very, very low energy gradient here. Right? It's not capable of moving a ball bearing sitting in an oil bath. Right? Not much friction there. So very low energy gradient. Okay? And we're going to use this threshold height in all the experiments to follow. Okay? So we fix this threshold height. We know what it is. The idea being, of course, that if we can still show an effect with the magnet, right, where that magnetic field is so weak that it can't move the single ferrous bead, it certainly couldn't be enough force to be moving that whole system around. Right? It must be pulling some of the energy from elsewhere, right? Clearly from the electrical field. So the experiment looks like this. We have our source. There's our tree with our one ferrous bead on it. Okay, so the orange bead is the ferrous bead. We're going to gate that down so we only have oscillation. Right, so it oscillates back and forth. For purposes of measurement, we're going to divide this thing into two states. It's either on what we'll call the magnet side or not on the magnet side. Okay, very simple. Half the time, the magnet will actually be there. We'll still call it the magnet side. The magnet will actually be there. The other half of the time, the magnet isn't there. What we're looking for is the probability of being on the magnet side and whether that's affected by the actual presence of the magnet or not. Right, so very straightforward. Hopefully that made sense. So at 3 different voltages, which turn out not to really play very much, low, medium, and high, we'll call them, the probability of being on the magnet side when the magnet is present is much higher than when the magnet is not present. Right? Super clean. Right, so what's happening here is that the system, right, being in a dissipative structure, it's actually more sensitive to the magnetic field. Right? Because, presumably, it's changing physical properties of friction coefficients or something, right? It's changing physical properties, it's not magic or anything, right? But it's more sensitive when it's in a dissipative structure. In a way, that is reminiscent of biology, at least in our opinion. Right? So for us, we want to argue that the poised state results from being in a dissipative structure. Any question? Okay.
Yeah, did you end up measuring just maybe a sole Ferris speed in the dish to see if the probabilities were similar? Because if they are, then it might be that it was just pulling it, but...
I'm sorry, I don't know what you mean. So like, sole Ferris speed...
Like, so you mentioned that having it be in a dissipative structure made it more likely when the magnet was present to be on that side.
Right.
So I'm wondering if lacking that dissipative structure and just having the bead...
Yeah.
You know...
Right, so I see your point. The problem with trying to do that particular experiment is that the Ferris speed alone, right, if you just put charge on, it won't go anywhere. It's just going to sit there. So unless it is part of a dissipative structure, it's not going to move at all. See what I mean? So the argument is all about, well, we had adjusted it so that the magnetic field was so weak that it couldn't move that single bead. We use that same field exactly here, right? But I see your point, and I think you'll see we're going to jump to chemical systems next, and we actually, there we have the opportunity to sort of have that exact setup. So maybe that will satisfy. Yes?
I wonder how this result changes if you change the number of beads of non-ferrous particles.
Yeah, sure. Yeah, we haven't explored that. It's a great question, right? Yeah. So at some point, surely, one bead isn't going to be enough to run the whole system, right? And we haven't explored that yet. Yeah. It's a great idea. Yes?
I must have missed something here. So the experiment, did you do anything with the gates, or no?
The gates are just to sort of make it a one-dimensional system. So when I say spending more time, I mean that. So this thing would naturally oscillate. It's going to go back and forth.
So why, when there's no magnet, why isn't it 50-50?
It's just due to the asymmetry in the setup. I mean that for whatever reason, in this particular set of runs, it happened to prefer to be slightly to one side than another. It's so the actual tip of the electrode, right? It's here it's an abstract point, but it's an actual physical thing, and it corrodes, it degrades. It's under a lot of pressure.
So it's really some kind of sensitivity, some kind of...
Yeah, it's just how the field set up in this particular setup. Yeah.
It's a similar question. I was saying, you don't think the gates have anything to do with the probability?
Do the gates have anything to do with it? No, the gate
have anything to do with if you change the position a little bit?
We certainly could do the same experiment by moving where we're locking it down around the ring, and we would find different base rate probabilities, right? But we would find the same. At least we think we would find the same separation, right? So it's not the raw probability that we're interested in. We're interested in the difference between the no magnet and the magnet condition, right? So whether it prefers slightly to be on the just to the left of whatever arbitrary line we've chosen, or just to the right of it, that again is something that's from this particular setup. Remembering this is a real physical system, it just has asymmetries built into it. Okay. All right. So this is the electrical side, and it's relatively simple. Right? I mean, we can measure the rate of entropy production in a very direct way, right? Just by having the current go through the system, we measure the current. But ultimately, to answer the sort of questions we want to answer, we've got to move to the chemical side of things. Right? We want chemical dissipative structures. Because ultimately, we want to talk about the link to biology. And so this is exciting and challenging. chemists are wonderful people to work with. They have a lot of answers. We need to be able, we think, to store energy and release energy on multiple timescales, and chemistry is a wonderful way to do that. It allows for the double-edged sword of tremendous complexity. Right? The good and the bad often go hand in hand. The thermodynamics, right, to actually make thermodynamic measurements of this system is pretty tricky, right? And it's something that we're slowly working our way towards. The system that we're using here are benzoquinone particles, which I'm going to call BQ particles. And what's happening here is we have, the reason they're moving, right, they're just on a aqueous surface. They are at, as the chemists say, at the air-water interface. That's how they like to talk about it. So they have a slow release of energy as these particles are dissolving. The system will eventually just die out because there's no flow in here, right? Unless you put new material in, all the energy is in the particles themselves. So it's a little bit different from our system, at least in feel, thermodynamically. I'm assured that it is equivalent. So the motion here is all being driven by surface tension gradients. So what happens is we get initially symmetry, right? That symmetry breaks, the surface tension gradient is different in different places, and that's what drives motion. So that is a phenomenon that's well understood and quite a bit is published about. So we get, with these guys, we get what we call flocking behavior. Literally, these guys come together and they kind of hang together, which is interesting. It's a little bit of a mystery why exactly they're doing that, and I don't think we understand that fully yet. But they clearly are staying together more than they would if this were like Brownian motion or something. And we can contrast this case, these irregular particles, and you can see they've just been kind of broken up more or less at random, where we have exactly the same amount of BQ in the dish with this case, where we have circular particles. Right? And the phenomenon is, it's not that they don't interact, they maybe even interact in ways which aren't Brownian, but they don't really flock together in the same way. They don't form coherent sets like these guys seem to. Right? So there's sort of this intermittent coherence to them in the irregular case. We don't get this in this, what we'll call circular case. Right? Despite the fact that it's the exact same material, the only difference here is the shape. Exact same amount of stuff. So we were interested in whether we could kind of see the flocking. Right? It felt like flocking when you looked at it, but we wanted to quantify it. This turned out to be a real pain in the tube. So a flock, we can think about it as a spatiotemporal structure that's characterized by intermittent, that is, once in a while, cohesive behavior. I mean, it comes together, and then somebody will drift off, and then they'll come back together. Okay, so it's not exactly like the trees where they kind of come together and they stay together. So we wanted to quantify flocking and really see that there was a difference between these two systems. So we could say at a minimum, a flock is when two or more particles are within a particular radius. So then we systematically increase the radius, and flocking will be shown by a nonlinear increase in the probability of being in a flock. And we should see a difference between our irregular case and our circular case. All right, so if we start out with some radius, at some radius, we will start having this particle is now in a flock. Right, so you can, without going into the details, you can imagine that we do this for each and every particle, for each and every frame, for the entire movie. Okay, fun way to spend an afternoon, or maybe 6 months. So here we have that analysis, right, where we have the probability on the y-axis of being in a flock, defined as 2 or more particles, as a function of radius for particle collections of various size. Okay, so on the right-hand side here, we have the irregular particles, and you can see that there's a very clear difference. Here we have 2 particles, 4 particles. When we get to 6 particles and up, we have a very strong nonlinear increase all of a sudden in the probability of being in a flock at a particular radius. Right? We don't see that in the circular case. There are hints of it here and there, right? Particularly at the larger particle sizes, but these seem to be very clearly we feel like we've gotten some quantification of flocking. At the moment, all right, we're not exactly sure why we only see this for particles with 6 particles and greater. It seems like there's some sort of critical mass that we need in order to see this phenomenon. We have evidence that we're not quite satisfied with. It's sort of a project we're still working on, which suggests that this irregular BQ system, the one that shows us flocking, which we think about as a dissipative structure, is showing us higher rates of entropy production. Right, so we really think that the flocking, we're thinking about that as a dissipative structure. So, yes?
So the spherical particles,
Yep.
they are flocking, is it something to do with Laplace's law?
Can you say more on that? Maybe. I don't know. Not that I know of, but it could be.
Yeah, because like the spherical surfaces, they usually lower the surface tension.
Yep.
Like they minimize surface tension. So is it something because of that?
It could be. It might be that simple. The problem with explaining flocking is that they should it seems that they should actually be repelling each other, right? Because they should be moving away, right? They should be moving to lower areas of surface tension, right? And yet they're all moving to lower areas of surface tension, and they are dissolving. Right? They should actually be moving away from each other.
Yeah. The circular cases actually show that kind of.
And the circular case, and in fact, there's a whole literature on these sort of dissolving particles where they'll actually, like, you put them in these circular canals and they'll stay in antiphase, for example.
Mm-hmm.
They'll chase each other around, right? But when you break the symmetry of the particle shape, right, then you get this flocking behavior. So there might be something there, but I'm not sure. Yes.
So when we look at the shape as they round,
Yeah.
if you imagine like they come in contact with each other,
Yep.
it will be just at one point. So where on the other stuff,
Yep.
you have more chance of one laying on another, I guess
I see.
that might also explain
Yep. Thank you.
why.
Yep.
Yeah.
Yep. That's a very good suggestion. Yep.
What happens if you have 2 very long pieces? Just 2.
Two pieces of BQ that are very
Long,
that yeah, I don't know. That's a good question. Yeah, we haven't played with that. Yeah, we haven't. There are lots of things we haven't tried.
And
That's one of them.
I assume that the round ones eventually become irregular as they dissolve.
They do, yes, and there probably is we haven't looked at that in particular, but there probably is an increase or change in how they're interacting as that happens. Yeah. Thanks, those are all very, very astute questions. So we're interested in whether, we're kind of excited about this sensor result from the electrical side. We're interested in whether we could get sensors to work in this side too, right? These are supposed to be analogous dissipative structures. So we did pretty much the same thing. We're trying to get a sensitivity to secondary gradients. Again, it's going to be a magnetic field. And show that by having one element which is sensitive to that magnetic field, that we can control the whole flock. Like that was the crazy idea. Right, so we took one little particle, we embedded some iron oxide in it, okay? And then we took our magnet and we adjusted the magnet height so that it didn't, to the point where it didn't affect the motion of the BQ particle. Now the BQ particle is already moving, so it's not like we have to sweep the magnet. The BQ particle is quite active, okay? So we're finding this threshold height. And it's the same kind of procedure that we did with beads. Right, so we're finding that smallest distance. Right, so only one of 15 particles is going to have iron oxide, and all the other ones are just regular BQ. They could care less about magnetic field. Really could care less. So we are going to then introduce the magnet, right, after some initial period of formation at that height that shows no effect on that single ferrous BQ particle. Right, so here we are. You can see we have pretty reasonable flocking behavior. The magnet comes in here, it's just a fixed magnet on a little stage. then it very convincingly takes control of the entire flock, even though only one of them is sensitive. Right, I found this to be very interesting. Right, it's a much less coherent structure, and yet here it is. Right, so we were completely surprised that this works so easily. Literally works the first time. Okay. Because we have the circular case, right? We actually have this very interesting control. So here the flock is very clearly being directed by the gradient. Right, so here we have the circular case. We can do exactly the same thing. Right? Run the exact same experiment, except these guys don't flock. All right, so again, so here comes the magnet, and here she's actually going to make our chemist college are actually going to make a couple of adjustments in the video a little bit after things start. Right, but we don't. It doesn't seem to take control in the way that this does. Right? Yes.
So this question is more of like philosophical question.
Okay.
Like so, I mean, if I got it from what you're saying the two systems are the same, right? Because they both have the leaky material.
Yes.
But the shape is the only difference. The shape of the
yes, let's say that's true. Yes.
Yeah, but one can argue that because there's different shapes in the two systems, we
Right.
can't say they are similar or the same. What do you think about that?
Well, sure. I mean, depending on how you wish to define, system and sameness, sure, absolutely. So our chain of logic, is speculative, right? We are saying that the reason that we get the sensitivity to this very and sort of demonstrably very, very low and ineffectual magnetic field is because the dissipative structure is changing something about the sensitivity, right? Literally, perhaps like the forces that the motion is generating in the system, right? So we think that's true. We then have a system that doesn't flock and seems to be similar in all other ways, at least in terms of its materials, right? But do we know for sure that that's what's happening? I don't think we certainly don't, right? It's suggestive of the idea that dissipative structures might be, but is it drop dead evidence?
Are those discs rotating, or is that just my imagination?
I don't know if they're rotating. That's a great question. They probably are. I would be surprised if they weren't. These guys are certainly rotating. Yes. All right, so I have one more thing to show you, and then I will let you know. So the last thing I want to show you is going back to the electric system, right? We have the ability to have these systems be sensitive to a secondary gradient. We are interested in whether we could get the system to go against the predominant gradient. Right? So one of the things that is, in some ways, the holy grail of this sort of work is, well, can you have the system climb a hill? Right? Will it go against the prevailing gradient? Right? And we thought that by using the sensor, we might be able to have it go against the gradient. Okay? So what we're going to do is we're going to create a system in which there is a low energy region and a higher energy region. We are then going to have, and in between them, I should say, is a kind of dead zone, right? A low energy region where the system will not go on its own. Okay? We're then going to couple the high energy region to the magnetic field. Right? We're literally going to have them be coincident in location. Right? And the question is, can we get the system to go through the low energy region given the presence of the magnetic field, with the magnetic field? Right? So it's going to look like this. Right? So the lower energy region, higher energy region, right? These are actually two source electrodes. We're going to start the system off in the lower energy region. This zone in between is a zone that it will not cross on its own. All right, we're going to gate it on this side, otherwise it just escapes around the back end, which we don't want. We'll run the experiment. And then at some point in time, right, after we've established that this guy won't escape, won't go through this dead zone, we're going to couple it with the magnet. We're going to put the magnet in. You'll see that's going to be indicated by this little red thing showing up in the film. let me start this off. It's a little bit long. So here's our tree. So this is orient you. This is our gate, right? The tree is in this low energy region. This is one source here. The other source is here. The magnet is going to come up underneath here. You won't be able to see it, but you will see a little red cap emerge here. And so what we're establishing at this point is that it approaches the edge of that region, right? Approaches the edge of this region, and then will head back the other way. It won't go through on its own. Okay. And then it's going to get to the gate. When it gets to this gate here, right, we will have you'll see a red cap will come up here, which indicates that the magnet has now been moved to this threshold, should call it sub-threshold level, right? Again, where the level at which we could no longer move that single Ferris bead while sweeping it across, right? So it's very, very low energy, right? So here it is coming, right? So now the magnet is up. So it gets
beads in oil.
It's the same situation. You have beads in the oil, slightly larger ring in this case.
Why does it look like there's oil that's flowing?
There definitely is oil flowing. Yes, so the oil actually convects.
Due to the electric field?
Yes, so the field comes down. We think it's depositing the ions on the surface, and it's creating convection. Right? But here we have it. It's gone through this dead zone, right, and goes up gradient, right, to find, in this case, to find a stronger source. All right. So, sum up. We're arguing that dissipative structures, including things like biological structures, seem to be intrinsically end directed in a way that allows them to increase their energy flow. We can see this in both electrical and in chemical systems. They seem to behave in a way that increases the rate of entropy production. We can get sensitivity to secondary gradients, so in a way that they're able to be sort of in contact with their environment very easily. All we need to do is to kind of forget that we're in the lab for a second and allow ourselves to create heterogeneous dissipative structures. That is, have a variety of materials. By having a variety of materials that form into dissipative structures, we get sensitivity to gradients that are that those elements respond to, essentially. So the heterogeneity in the structures turns out to be important, and this is sufficient to affect the global behavior of the system, even to the point of going up gradient, that is, going upstream. Okay, thank you very much for your kind attention.
Thank you very much. We have lots of questions in the middle, but we can take a couple more.
Okay, so with the BQ particles, so the thesis is that it's maximizing the energy production. And so the BQ particles, the flow of energy through the system was chemical energy.
Yeah.
So does that mean that, were you measuring the rate of flow in terms of chemical energy?
Yeah. So this is difficult to do. It's possible. In the BQ system, we have it's like 100% dissolving, right? So there's like no evaporation at all. So we can actually take the concentration, the change in concentration of BQ, and measure it and use that as as an approximation of rate of entropy production. We've tried that, but I'm not saying it's not without problems. It's really hard to do. So you don't want to affect the surface. It's a surface tension system. So the last thing you want to do is affect the surface, right? And so it's kind of hard to get a measurement out of it without affecting the surface. So we've been trying, but so we have some preliminary evidence where we think we can show that there's an increase in the rate of entropy production. We have the flocking behavior, but it's messy, and we're trying other ways.
You could also maybe look at the interval instead, and just like if you fix it,
yeah.
If you fix all the particles
yeah.
somehow, does it take longer to dissolve than if you let them move around?
Yeah, that's good. Yep. No, that's
So,
good.
yeah, I can imagine.
Yes.
How do you make those discs?
She has a pellet press
Okay.
where she had to buy special dies to make the disc. Yeah. So the BQ system, was that initially they thought they could do electrochemistry with it. And in fact, it's a much easier system to use. It's camphor particles on water, do a whole bunch of really nice things, make much better structures. But they wanted to do this electrochemistry thing. It never worked. So you couldn't do electrochemistry, even though in the literature it says you can. Anyway, so it's a long story, but yeah, the BQ it turns out that it's got some interesting features now, but boy, it took a long time to get there. Yes.
This was a very interesting talk. Thanks very much. I had two questions. One is when you alluded to it a little bit at the start of the talk, there's two different ways that you could sort of look at what the system's trying to achieve, trying to maximize entropy.
Yep.
And that's not maybe the only way to consider it, because really the system ultimately wants to, I would think, and you're saying also increase energy flow, but in these systems, are they not trying to minimize their energy, in particular in the first structure? Is not a better way to also,
well,
not a better way, but a potential way to think of it?
So they're minimizing the potential, right? But that is the dual of increasing the rate of entropy production,
Okay.
right? So energy consumption, right, implies entropy production.
Right. And it's trying, so normally we think high entropy reduction is high irreversibilities in the system. There's a lot of losses in the system.
Yeah.
That's what it's trying to achieve. That's the theory.
Well, that's true if the energy consumption is constant, right? Then actually being a crappy system, right? It would be preferred. But that's a good question. I mean, I don't think we want to say that, right? I mean, I think that seems counterintuitive to the biological.
Maximizing energy flow that means maximizing energy flow.
Yes, yeah, and which thermodynamic quantity is the right one? It's very much open to debate, and there are people who feel very strongly that this is not the right way, and other people feel very strongly that this is. So we're quite neutral, and we don't. It wouldn't surprise us if if it is something else. It is the rate of entropy production scaled by something. I don't know.
And my second question was just that was a really interesting experiment with BQ particles. When they showed flocking with the irregular shape, is that actually trying to reduce its entropy? That they're trying to form order through flocking? Is that trying to move to a more ordered state? So by flocking, or is that not the
well? So all dissipative structures are more ordered. I mean, they've gone from more random to more ordered internally, right? So it's important not to get the entropy as disorder argument mixed in here, because it gets really confusing, right? So entropy really has to be thought of in that phenomenological sense of energy, essentially waste energy coming out of the system. If you think about it as, it is certainly more ordered. So when they talk about there being order, this being an order-inducing process, that is absolutely true. It's breaking symmetries. It is becoming more ordered, right? And that, of course, that's part of what we love about it, right? Is that because we want biological systems to be somehow self-ordering. Thank you.
Any other last-minute questions? Yeah.
Yes.
The last one. Okay.
This is going to be out of what you're explaining, but what would be the application of those sort of findings?
That's a great question. I wish I had a good application that I could patent or something. But so what's the application? So we really are going for very big picture questions about biology. Right? Now, it could be that if we could find this principle, right, and we could say it just right, and then you could show how to measure it in biology, right, then you'd really have something. You'd essentially be saying, this is the principle that biological systems are doing in their own self-regulation. When we have breakdowns in biological systems, it's because they're still trying to satisfy this principle, but they're not doing it in a way that now is promoting their long-term survival, right? So I think ultimately the questions are going to play back into the biological world, but that's probably going to be long after I'm dead.
All right. Thank you very much again.